right, we got the final objective for Unit 4, Objective 6, graphing rational expressions. Now, like it says here, like every other graph we've investigated in this class, we'll start out with the parent graph, or the parent function. Okay, so again, the parent function is just the simplest form of an equation that we can get. So if our equation is going to be a rational expression, what's the simplest equation we can come up with? Well, 1 over x is about as simple as it gets. Okay, and remember, you can think of this as y equals 1 over x. All right, now, what does this graph look like? Well, we don't know, so how can we graph anything? Well, we can make a table, and it's not always the most efficient way to get our graph, but it will always work. Now, before we do that, though, let's look real quick at this fraction. Well, what are a couple things we notice about this fraction? Well, for one, since x is in the denominator, and only x, well, what can x not equal? X cannot equal 0, right? Because we can't have a 0 in the denominator. So then that's going to give us an asymptote, which hopefully you remember what that is. It's just like a boundary line. So the line x equals 0, which in this case is our y-axis, is going to be a vertical asymptote. Okay, so our graph can never touch that line. Is there anything else that our function cannot equal? Well, let's see. If x is something like 2, it's a fraction, it's a small number. If x is 3 or 4 or 10 or a million, well, okay, it's a small number. So x can be a really, our function can come out a really small number. In other words, y can be a really small number. Can it be a big number? Well, sure. What if x is like a half? 1 divided by a half is 2. Or 1 divided by 1/5 is 5. Or 1 divided by 1/1,000,000th is 1 million. So x can be a really small, our function, y. It can come out a really small number, or it can come out a really big number. But what can our function never come out? Well, 0. Because in order for our answer to be 0, when does a fraction equal 0? Well, when the numerator is 0. When's the numerator here going to be 0? Well, never. It's a 1. So we can make this a really small number. We can make this a really big number. But this thing can never come out 0 for y. So then we're going to have a second asymptote, a second boundary line at y equals 0, which is basically just the x-axis. Okay, so if there's no shifting going on in our function, then the x and y-axis are going to be our asymptotes. Okay? In other words, our graph is never going to cross either of those lines. That's going to break our graph up into 2 pieces. Okay, so great, we know that, but what is our graph going to look like? Okay, well, we don't know, so let's start by plugging in some points here, and then see what we're going to get. We're going to plug in a couple positive values for x, a couple negative values for x, and then hopefully that'll give us an idea of what our graph is going to look like. Okay, if I stick in x is 1, well, stick in x is 1 there, and I get 1 over 1, which equals 1. Okay, so then that gives us the point 1, comma 1. Okay, great, there's 1 point. Let's pick another positive value. How about 7? If I stick in 7, I get 1 over 7, which we can't simplify that. We just get the point when x is 7, y is 1/7. Okay? All right, what if we plug in a fraction, a small number, like 1/5? Well, then I get 1 over 1/5. And remember, dividing by anything is the same as multiplying by its reciprocal. So then this is the same as 1 times 5 over 1, which is just 5. So then I get the point 1/5, comma 5. Okay, so there's a few points by plugging in positive numbers. Let's plug in a few negative numbers, and hopefully that'll give us some more points. If I stick in x is -1, then I get 1 over -1, which is -1. So when x is -1, y is -1. What if I stick in -7? Okay, then I get 1 over -7, which again, we can't simplify that. So when x is -7, y is -1/7. Okay, there's another point. And then if I stick in x is -1/5, I get 1 over -1/5, which is the same as 1 times -5 over 1. Need parentheses there, otherwise it looks like we're subtracting. And then 1 times -5 over 1 is -5. So we get the point -1/5, comma -5. All right, so we got 6 points there. Let's plot those and see if we can see what our graph is going to look like. All right, so first we got the point 1, comma 1. So we'll go over about 1, up about 1, right about there. All right, next we're going to go over 7, about here, and up 1/7, so up just a tiny bit. We'll say it's right about there. Next, if we go over 1/5, which is over just a tiny bit, and then up 5, over a tiny bit, up 5 is going to be, I don't know, right about there. Okay, then we got a few points. Okay, so we can see part of our graph is going to maybe look like some kind of curve here. And then if we plot these points, we get negative 1, comma 1. It's going to be right about here. Negative 7, comma 1/7. So back 7 down a tiny bit. It's going to be right about there. And then negative 1/5, comma negative 5. So over to the left a tiny bit and down 5 is going to be, I don't know, somewhere about there. Okay, so we got these two sets of points. And then what is our graph going to look like? Well, remember, since it can't cross either of these lines, it's going to actually be two curves that look something about like this. All right, so it's going to approach these asymptotes, but never quite reach them. So it's going to be these two kind of back-to-back curves. And that's what our parent function is going to look like. So remember, every other graph that we draw is going to look like some version of this thing. It might be shifted around. It might be a little further away from the axis. You know, it might be flipped around, but it's always going to resemble this graph here. Okay, so this is the parent function of our graph. A good idea, if you want to, press pause and then go to Desmos and then type in this equation and it'll give you a more accurate graph of what that looks like, but you know, that's pretty close. Okay? All right, let's answer some questions below here. Every graph we've graphed has had a key point. Sometimes the point has a specific name like the vertex, other times we just call it the most important point. What would you say is the most important point on this graph? Well, probably where our two asymptotes intersect. Here it happens to be the origin, but it's not, you know, it doesn't have a name. It's not always at the origin. But for this particular graph, the most important point, we would say that's at 0, 0. Again, where those asymptotes intersect. Notice a few things about this graph. In its present state, it never touches the x or y axis. These are the asymptotes. Again, there's like boundary lines. State the equation of the horizontal asymptote. So what's the equation of this line here? Well, we talked about that when we drew it. That's the line y equals 0. What's the equation for the vertical asymptote? So this one here, we talked about that again. That's just x equals 0. Okay. So anytime, just bringing this up, anytime there's a vertical or horizontal shift, that's going to change your asymptotes, which is going to change the equations of your asymptotes. So your equations of your asymptotes are pretty much the same as your vertical and horizontal shifts. We'll talk about that when it happens. All right, next. State the interval or intervals on which the graph is increasing. So when is my function getting bigger? In other words, as x gets bigger, when is y getting bigger? So let's see here, it's slowly decreasing, quickly decreasing. Okay, and then quickly decreasing, and then slowly decreasing, slowly decreasing. Okay, so then this is always decreasing, it's never increasing. So then for this line here, we could just put, well, no solution, because it's never increasing. Okay, when is it decreasing? Always, right? Pretty much, except, and again, if we're listing an interval, it's the x values. Well, what can x not be? X can't be 0. So then we got to split it up and we got to write it like this. X is decreasing from negative infinity up to my asymptote, which this happens to be at 0. And then union with, and then we want parentheses around the 0 because we're not including 0. And then union with everything from 0 to positive infinity. So basically we just have to exclude x. It's decreasing everywhere except at the asymptote where x is 0. Okay? Next, state the intervals on which the graph is less than 0. Okay, so what they mean by less than 0, another way to say that would be a negative number or below the x-axis. So then where is our function up here below the x-axis? Well, this half of it. Okay, and again, the interval is from negative infinity because it's always underneath the x-axis. It never crosses that asymptote up to here, which is at x equals 0. So like I just said, it's less than 0 from negative infinity to 0. Okay. Next, when is our function greater than 0? In other words, when is it positive? When is it above the x-axis? Well, that's this whole piece here. So from 0 to infinity. All right, almost done. A couple more questions here. State the domain and then state the range. So on my graph, what can x be? When does it stop going to the left? Never. When does it stop going to the right? Never. So what can x be? Pretty much anything except for 0 again. Okay, so then the shortest way to write that, we could write it just like this, from negative infinity to 0, union with 0 to infinity. But a quicker way to write that for the domain, it's perfectly fine to write it this way too. X is not equal to 0. And that implies that it can be anything except for 0. Okay, then what about the range? Let's see, my y's, they go down forever and they go up forever. So y can be pretty much anything except for 0 again. Okay, so again, we could write it like this in interval notation, or we could just say, okay, for the range, well, y cannot equal 0, and that's the shorter way to write it. Okay, so then there's our domain and our range. Next, use the definition of the y-intercept, which is make x equal to 0, to demonstrate why the y-intercept does not exist. So let's see, our function is y equals 1 over x. And then, well, if we stick in x is 0, that leads to, so this little double barred arrow means this leads to, it kind of shows the next step in the problem. Now we get y equals 1 over 0. And then what is 1 divided by 0? What's anything divided by 0? Not 0, it is undefined. Okay, and if you have any questions about why it's undefined and not 0, we can go over that in class, just let me know. Okay, so that's why here we don't have a y-intercept. Okay, and then it says use the definition of the x-intercept. In other words, make y equal to 0 to show why an x-intercept does not exist. Okay, so here, adjust the camera a little bit. Again, our function is y equals 1 over x. And then if we stick in y is 0, because 0 equals 1 over x. So, you know, we talked about this in the beginning. When is this fraction going to equal 0? Well, when the numerator is 0. When is the numerator going to be 0? Never. It's a 1. Okay, so this, you know, it just simply can't happen. All right, so that doesn't mean we're always going to have no x and y intercept. If we shift our graph around, then yeah, sure, we can cross the x and or y axis. Okay, all right, there's the first page. Let's move right on to the second page. All right, here we are. All right, so example 1. Consider the function of y equals 1 over x minus 3. They want us to sketch this graph. So sketch means we don't have to plug in a bunch of points, make it exact. We just want to make sure, you know, our asymptotes are in the right place and our graph is about in the right spot. Okay, what's the most important point going to be now? Normally it's at 0, 0, but think back to unit 1 and unit 2. If I subtract 3 from my x's, then what is my, you know, shift going to be? So think like a parabola. Y equals x squared. Where's my vertex for that? 0, 0. What if I had this? X minus 3 quantity squared. Where's my vertex going to be now? Well, that's going to move me right 3. So that's going to be at 3, 0. Okay, that shifting thing works the same exact way here. If I subtract 3 from my x's, that's going to move my asymptote to the right 3. So now instead of my vertical asymptote being at 0, 0, well, that's going to be shifted over right 3. So we're going to go over 1, 2, 3, and then there's going to be my vertical asymptote. And then I didn't add or subtract anything from the end of my equation. In other words, I didn't change my horizontal asymptote. So my asymptotes are now going to be at x equals 3 and still y equals 0. All right, and our most important point now, rather than our asymptotes intersecting at the origin, well, now they intersect at 3, 0. So we're going to call that 3, 0 for the most important point. Which asymptote did we move? Well, the vertical asymptote. Okay, and then now we can sketch this. And remember, our graph is going to look like it did before. It's going to look just like this thing. The only difference is it's shifted to the right 3. So we're still going to have a curve in the top right section that's going to approach the the vertical asymptote and the horizontal asymptote, and a little curve in the bottom left section that's going to approach both asymptotes as well. So once you have your asymptotes drawn, Well, now we can give a sketch. And this is, we don't need any particular points. It's just going to look something about like this. That and something like that. Good enough for a sketch. Okay? All right, the graph still does not have a blank intercept. Which axis do we still not cross? Well, we crossed the y-axis right there, but do we ever cross the x-axis? Well, no, because our horizontal asymptote is on that axis. So we do not have an x-intercept. Okay, but it does have a y-intercept. We want to find that and label it on our graph. Okay, so then how do we find the y-intercept? Okay, well, it's right there, so we know it's negative something because it's definitely below the x-axis, but how do we find it? Well, just like we always do, we want to stick in x is 0. All right, so our function is y equals 1 over x minus 3. Okay, and then if I stick in x is 0, we get y equals 1 over 0 minus 3, which gives us y equals negative 1/3. So yeah, like we said, it was negative something. It was a little bit below the x-axis. Okay, so then that gives us the point 0, comma, negative 1/3. Okay, so there is our y-intercept, and like we said, there's no x-intercept. State the equation of the horizontal and vertical asymptotes. So the horizontal asymptote, well, what's true about every point on this line? Well, it's y equals 0. And the vertical asymptote, what's true about every point on this line? Well, x equals 3. Okay. Next, state the intervals on which the graph is less than 0. So where's our function below the x-axis? Where is it negative? Well, this piece here again. And then where is that from? From what x value to what x value? Well, from negative infinity up to our asymptote. It's always going to be up to the asymptote. Okay, so then it's going to go from negative infinity up to positive 3. State the intervals on which our function is greater than 0. In other words, above the x-axis. Well, that's this piece up here. So from our asymptote to positive infinity. So from 3 to positive infinity. Okay? And then that's it for that example. So the graphs really aren't that hard to do. Once you know where to draw your asymptotes, then you can just give a nice little sketch of our curves, and then we can start answering some questions. If you want to get a more accurate graph, well, you can always plug in points. I know my vertical asymptote and my horizontal asymptote intersect here at an x value of 3. I can plug in an x value of 4 and 5 and 6 and 3.1 or whatever I want to plug in, but you don't need to waste your time doing that. Just a little sketch is fine. Okay? All right. Example number 2. We're actually getting through these fairly quickly. All right, our next function is 1 over x plus 4 minus 5. So then what is the shift going to be for that one? Okay, well, this is going to move us left 4. And then subtracting 5 from the end is going to move us down 5. Okay, so our shift is going to be left 4 and down 5. We want to sketch the graph and identify the horizontal and vertical asymptotes. Okay, so let's see. Let's sketch it first because that's probably easier to do. Normally, we're right here at the origin. That's where our two asymptotes, that's where our two asymptotes intersect. Well, now that intersection just got moved left 4 and down 5. So let's just go left 4. So 1, 2, 3, 4, and then down 5. 1, 2, 3, 4, 5 will be right about there. And then basically, once you have the intersection of your asymptotes where that point is, which again is just whatever your shift was, then you need to draw a big cross right there. My horizontal asymptote, my vertical asymptote, so what I'm drawing first, it's going to be here at x equals negative 4 because we shifted left 4. And my horizontal asymptote is going to be here at y equals negative 5 because we moved down 5. And then what's my graph going to look like? Well, just like the other one did. Top right and bottom left, I'm going to have a couple curves that approach my asymptotes. Okay, so it's going to look something like this. And something like that. Okay. All right, those aren't perfectly mirrored, but that's okay. Again, it's just a sketch. All right. All right, what are the equations of our asymptote? So our horizontal asymptote, we just said that as we drew it. we're down 5, so then y equals -5 everywhere on that line. Our vertical asymptote is always x equals what? And our shift, we move to left 4, so it's x equals -4. Everywhere on this line, x equals -4. Does the graph have a y-intercept? Sure, we hit the y-axis right there. We can see it's just a little bit above our asymptote, so it would be, a little bit bigger than -5. So yes, it does have one. And then it wants us to find it. Okay, so then how do we find the y-intercept? Well, like always, we stick in x is 0. So my equation is y equals 1 over x plus 4 minus 5. Now, we don't have a ton of space, so we're going to stick in 0 right away for x. And we get 0 plus 4 minus 5, which gives us y equals 1 over 0 plus 4 is 1/4 minus 5. And then -5 plus 1/4. So if we're down 5, we go up 1/4. That's going to be at -4 3/4. Y equals -4 3/4. I'm going to put 4.75. We'll do a decimal. Okay. So then our intercept is at 0, -4.75. There's our y-intercept. Okay. Next, do we have an x-intercept? Well, sure, I crossed the x-axis right there. It looks like it's 1, 2, 3, somewhere between -3 and -4. So that's kind of what we're expecting. But let's actually solve for it and find it. And how do we solve for that one? We want to stick in, so we're going to put it way over here so we have room to work. Yes, and then we want to stick in y as 0. And when we stick in y as 0 to our equation, we get 0 equals 1 over x plus 4 minus 5. Okay, this one we'll try to show our work. We're not going to have a ton of space. We got to write kind of small. If we start by adding 5 to both sides, that gives us 5 equals 1 over x plus 4. And then we have a couple options to solve one way. Let's think of this as 5 over 1. And since I got a fraction that equals another fraction, we can cross multiply. 5 times x plus 4 gives me 5x plus 20. Equals that times that, which is just 1. Okay. Next, subtract 20 from both sides. Sorry, I'm writing so small, but we want to make it fit. So that leads to, we get 5x equals -19. And divide both sides by 5. And we get x equals -19 over 5, which that goes in there what? It's 3.4 equals -3.4. Okay, so then our x-intercept is at -3.4 comma 0, which, yeah, like we said, it looks like it's somewhere between -3 and -4, so we're feeling good about that answer. Sorry about that. Didn't realize you couldn't see that. Okay. So sometimes there's a little bit of arithmetic involved, a little bit of algebra. But again, no matter what the shape is, to find your y-intercept, stick in x as 0. To find your x-intercept, stick in y as 0. But with these, look at your graph first and see if you even have one of those intercepts. Okay, you might not have to do the work. All right, let's answer a few questions at the bottom. We're almost done here. First one, state the interval or intervals on which the function is increasing. So when is this graph increasing? So let's see, slowly decreasing, quickly decreasing, and then quickly decreasing, slowly decreasing. So this one is always decreasing. It's never increasing. So we can just put the no solution symbol there. When is the function decreasing? Well, for all values of x that exist on our graph. So it's from -infinity up to what? Well, always the asymptote, which is at -4. So from -infinity to -4. Union with everything from -4 to +infinity. Okay. Next, when is our function less than 0? Okay, now this one's a little bit different than the last one that we had like this. When is our function less than 0? Well, this whole section is from -infinity up to our asymptote. So it's from -infinity to -4. But that's not the only part that's under the x-axis. What else is negative? What else is below the x-axis? Well, this whole section here, from that point there to infinity. And then what is this point? Well, we just found that point. That's our x-intercept. So from our x-intercept, which is at negative 3.4, and it doesn't matter if you use a decimal or a fraction, and I should not have put parentheses there. That's a giant comma. That's what that is. Comma, sorry about that, infinity. Okay, so that is just a big comma. So, sorry, I wrote in pen. I can't fix it. All right, next, where is our function greater than 0? That's what the next line says. Greater than 0 just means above the x-axis. Well, just this little piece right here. Okay, so it's always from left to right, from smallest number to biggest number. So that's from our asymptote to our x-intercept. So it's just that little part there, which goes from negative 4 to our x-intercept, which is negative 3.4. Okay. All right, next, state the domain and the range. Okay, so then what is our domain that goes down here? Sorry, I'm trying to keep everything in view. What is the domain? Well, x can be everything except for what? Well, negative 4, because that's what would give us 0 in the denominator. So x is not equal to negative 4. That's the easiest way to write the domain. Next, what's the range? Y can be everything except for what? Well, except for negative 5. Okay, because what would it take for y to equal negative 5? I have y equals something minus 5. Well, in order for the answer to be negative 5, this would have to be 0, which again can't happen because the numerator is never going to be 0. So y cannot be negative 5. Okay, and then that's that one. All right, hopefully you're keeping up with this. Again, to get a sketch, it's not that bad. Find out where your asymptotes intersect, and then you can draw your two curves. And then answering the questions can be the hard part. You just got to pay attention, especially if you got to find some intercepts. All right. Now there are other things we can do to the graph. What do other changes in the equation do to the graph? So it's not always going to be 1 over something. It might be, like 3 over x. What's that going to do to the graph? Now, what I would like you to do is go to Desmos. Again, hopefully you already did once. And put in 1 over x. Then change the 1 to a 3. Then change the 1 to a 5. Then change the 1 to a 50. And see what happens when you get that bigger number. And what you're going to see is your graph is going to get pushed out this way further. Okay? So it's going to be, further from that intersection of your asymptotes. So it's going to kind of make it a little bit wider. So the bigger the number is, the further it gets pushed out. But again, go to Desmos. You can very quickly change that number and see, okay, yeah, it gets wider and wider and wider. Okay? And then next, well, we've done the x plus 3 stuff. We've done the bigger number here. We've done adding or subtracting something to the end. These two numbers shift it. This makes it a little bit wider. What does the negative do? Well, what do you think it's going to do? If we have, going back to our little parabola example here, what's this graph going to look like? Y equals x squared. Well, parabola at the origin opening up. What if I had y equals negative x squared? What's that parabola going to look like? Well, same vertex, but it's opening down. In other words, it flips it. Okay? So same thing. Go to Desmos. Type in this equation, positive 2 over x plus 3 plus 1. And then add the negative and see what happens. And you're going to see very quickly, well, it's just going to flip it. So rather than our two curves being in the top right and the bottom left section, it's going to be in the top left, and the bottom right section. Okay? But first of all, there's more than just flipping it. Our asymptotes were shifted left 3 and up 1. So I would go left 3, up 1, and that would be the intersection of my asymptotes, which I'm going to draw with my highlighter here. And then, to draw my curve, I know it's going to be pushed out a little bit more than normal, but instead of in the top right and bottom left, well, it's just going to be in the top left and bottom right. And again, it's going to be pushed out a little further than normal. Don't worry about exactly where. If you're concerned about that, you can plug in a few points, but it's going to look something about like that. Okay? All right. Well, that wraps up the notes. Please ask questions in class if anything wasn't clear.